and we're about to have a look at electrical currents, energy transfer, and then move on to appliances and efficiency. Let's have a look at what we mean by electrical currents and charge. We've got a relationship between current, time and charge. We know that the charge flow, and this has got a lovely letter in physics, it's Q, and it's measured in something called coulombs, and this equals the current, which we have the letter I, measured in amps or amperes, times time, which will give the letter T, and this is, as usual, measured in seconds. So Q equals IT, and this is a way that we can measure the amount of charge that flows in a circuit. Now, we also talk about volts. Voltage, sometimes called the potential difference, and sometimes when you're talking about cells, it is the electromotive force. Potential difference, sometimes called the PD, electromotive force, sometimes called the EMF. Now, when a resistor is connected to a cell, so let's have a couple of cells here, and let's put in a resistor. There we are. Now, when we put this in, our resistor is connected to a battery. Work is actually done by this battery, and what it does, it makes electrons pass through this resistor. Each electron repeatedly collides with bits and pieces in here, transferring energy to the resistor. So these atoms, these ions, whatever they are in the resistor, gain kinetic energy. They vibrate even more, and this resistor becomes hotter. So the electrical work being done by this battery here is equal to the energy transferred to the resistor. In this way, we're transferring chemical energy in the battery to thermal energy in the resistor. So, when charge flows through a resistor, energy is transferred to the resistor so that this resistor becomes hotter. And we know our energy change here, E, is going to equal the charge flow, and the charge flow we called Q, times the potential difference, which we measure in volts, V. So E equals QV. Now, I also know that energy is power times time. and we know that power is the voltage times the current. So that gives us quite a few different sort of formulae we can play around with. So here we've got E equals PT. We've got power is volts times current, so E equals volts times current times time. With this bit of physics, there is quite a lot of formula to sort of learn and to relate. Let's look at this little circuit here where we're trying to put electricity into a resistor. And what I've got, a load of bits and pieces here to have a look at, and let's have a look at them bit by bit. Now, let's start with the easy experiment. So let's get out simply some wires and a resistor. So let's take my battery, my cell, and I'm going to get Paul to look at this little bit carefully. Now, we saw this in a previous video, but we'll bear this one in mind again. So I've just got it connected to one 1.5 volt battery, and as the electricity passes through, we notice this thermometer start to change colour. It's starting to change temperature, and it's now the chemical energy in the battery is being turned to electricity, and that electricity is here being turned into heat. And we can see it's gone up from 30 centigrade, 30 Celsius to 35 Celsius. Don't know if I can turn it a little bit more to help you. I'll put a piece of blue tack here, and that might make it a little bit easier for you to see. And we can see here we've gone up from 35, and electricity is still working, so hopefully it will go up to 40 in a moment. And there, this resistor is now getting up to 40 Celsius. We can see the slight colour change going on here. So here is our experiment to demonstrate that we've got chemical energy in the cell. It is being converted into electricity, and from electricity it's being converted into heat energy in this resistor. Okay. So this resistor gets hotter. We can't see the resistor, it's actually inside here because it's got this temperature plate put over it so we can actually pick up the heat. And I can feel here it feels warm, but that's not easy to show on the video. If we look at taking a different resistor, and it's not easy to see these resistors, So I've got one that I can open up, and inside is one of these small resistors. This one is 200 ohms, and if I connect that up to my battery, my cell, then if I touch this, I can feel that it gets hot. And I don't want to run this for long because this is going to get quite warm. So it's using up our energy. We've got coming out of this cell 1.5 worth of volts and some current. We're running it for some time, producing energy, and that energy is being used up by turning this into heat. And we see it also if we use this resistor. This resistor is simply a bulb, and if I connect it, it's going to glow not very well. So let's give this a little bit more chance to sort of do a bit better. There we are, let's give it 3 volts. And here we can see the chemical energy in these batteries, these cells, is converted to electricity, and we can see it here to light and to heat. And that one is perhaps a more easier demonstration of what we're looking at. Okay, so we've got some way of trying to convince you that we've got some energy transfer in a circuit. And when we're playing around with this idea of charge, we're talking about something called coulombs. I don't know what coulomb is. Let's have a look. So we'll have a look down here. Now we've got a circuit. Let's have a circuit, and I can set up here this being 12 volts. We're going to do this in a moment, and I'm going to put this in series with a bulb, and with this bulb then what we're going to do is we're going to put a variable resistor and we're going to measure here the voltage going across this bulb. Now let's think about what we've got in a series circuit. 12 volts goes through, it goes all the way round, but it's used up. So that if I've got 10 volts going through here and I've got 12 volts in total, then there would have to be 2 volts worth of sort of, well, I was going to say voltage, but basically we can turn that into joules. For each coulomb of charge that leaves the battery, we've got 12 joules of energy, and that is going to be the charge times the potential difference. 10 of those joules will be used up here in the bulb, and 2 of those joules will be used here in the variable resistor. The bulb becomes hot, emits light, the variable resistor becomes warm, and it heats the surroundings. So our energy is being dissipated both by the bulb and by this variable resistor. Let's see if we can create this. So what I'm going to do is I'm going to use the other circuit. I'm going to use, boringly, a mains power supply. And what we're going to do is we're going to bring that in here. So there's our power supply coming in. We've got a bulb and we want our resistor. And here is our variable resistor. And we can connect the rest of our circuit up. And it should light. What I'm going to do is I'm just going to take that out and I'm going to put a switch in its place, which is much better to use, so it only lights up as and when I need it. Now we're going to want a voltmeter. So let's take a voltmeter, and what I'm going to do is I'm going to put the voltmeter across the bulb as we did, and I'm going to put the now let's see if I can put these round the back, so hopefully you'll be able to see what's going on. If I've got it round the right way, here I've got, as near as I could guess, we've got 12 volts coming out of this power supply, and I've got about 9.89. If I adjust this, I've got about, on a minimum here, about 9.96, as near as I could get 10 volts going through, and that means that 2 volts, or 2 here joules of energy per second being used up. As I change the voltage here, I'm trying to do this so you can see, I'll come down there and you should be able to just about see the bulb. No, you can't. Let me adjust a little bit more. That might make it so you can see the bulb as I adjust this circuit. My problem is I've got the voltmeter in the way. You can just about see it, and as I adjust this down, the bulb gets much dimmer. Down here I've got just 1 volt going through. If I've got 2, we might just see the bulb is illuminated red. You can't see that. Let's turn this round. Now hopefully you can see the bulb a bit better. And you might, if Paul zooms right in, just see the bulb is glowing just very slightly red hot. And this is 1.94 volts. Paul's going to zoom out again for me now, so you can see the voltmeter. And as I turn this up, 3 volts, the bulb is brighter. 4 or 5 volts, 7 volts, 8, until it's at its maximum here, which is about 9.92, because this has got some resistance anyway, and we can see this is changing. So we can put more or less volts through each of these devices by changing this variable resistor to change its resistance. As its resistance goes up, more energy is being used in this resistor. Managed to sit down again. Okay, so energy transfer in a circuit. We've got energy being transferred, chemical energy in the battery, electrical energy in the wires and in the circuit, to the bulb, the resistor, where the energy is being turned into heat and maybe light. If we try to work out what's going on here, let's try a little sum to work out what's going on. So if we've got here working on our energy, let's try and work out what we've got, and let's suppose we've got here 12 volts, and I need to know my number of coulombs, and we know my coulombs is going to be my current times the time. So I didn't do in that circuit, I didn't measure the current going through, so we'll make it up and we'll say that, let's suppose it's 0.2 amperes and we ran it for 10 seconds. So the number of coulombs therefore is going to be I times T, which is going to give us here 2 coulombs. The energy is my 12 volts times my 2 coulombs, which is going to give us here 24 joules of energy put through the circuit. All this charge on the electron and what it was doing was discovered by a gentleman called John Joseph Thompson, and he discovered that around about 1900 sort of time, and he discovered the electron, and he showed that basically all atoms contain these negative particles, these electrons. First time they'd actually discovered them, and they discovered that the charge on just one electron was a minute amount. He discovered that it was about 1.6 times 10 to the minus 19 coulombs. To put that into perspective, that is going to be 0.123456789101112131415161718 6 coulombs. That is not a very big number. So that is the amount of charge on just one electron. We have our formula that the charge, coulombs here, equals the current times the time, amps time. And if I wanted to try and measure the energy going through, then my energy here is going to be this flow of charge times the volts. We can use these formula to work out a whole series of different problems. And let's just pick up a couple of these problems to try and solve. Let's suppose I want to find out that if I've got 5 amps of current and it flows for 4 seconds, then the amount here of charge flow, Q, is going to equal my 5 amps times my 4 seconds, which was going to give me 20 coulombs. What would happen if we ran 2 amps for 1 hour? Well, 1 hour is going to be 60 minutes, and that's going to be 3,600 seconds. Sad state of affairs when I don't actually have to work that out, that I can just remember that fact. So we've got to measure in seconds and in amps. So if I want to work out my charge here, it's going to be simply looking at one number times the other number, which is going to be my 2 times my 3,600, and that's going to give me 7,200 coulombs. So we can work out these things quite easily. If I want to try and work out what the energy transfer for that might be, let's suppose then I've got 2 amps running for 1 hour, and let's give ourselves a voltage of 6 volts. So our energy transfer, E, is going to equal Q times V. I've worked out Q, 7,200, times my voltage, which I've set at 6, and for this I'm going to use my calculator to help me, and this is just going to be 7,200 times 6, which is going to give us 43200 joules. Now, I don't like playing around with joules like this. It's better instead to change my joules to kilojoules, so that's going to give me 43.2 kilojoules, and that's only running, as we had, 2 amps at 6 volts for 1 hour. So it doesn't take long to get quite a large amount of energy. So this is our energy transfer. Usually when they give you a question like this, it might be something more like we've got, let's have a problem then, let's calculate the energy transfer. When we have, let's make some numbers up, let's have 3 amps for 60 seconds at 6 volts. So we can work out here my energy is going to be Q, and we know that Q is the current times the time times the voltage. So my energy here is going to be my current, which is going to be 3 times 60 times 6. And we'll go to calculator to work that one out. And we've got here 3 times 60 times 6. And that gives me 1080. Joules. Or we could write that as 1.08 kilojoules. So the things we need to remember from this are really not that difficult. We need to remember a couple of formula. We need to remember that Q equals IT, the charge flow. We remember that it basically gets hot, and we remember the energy transfer as Q times V. When the charge flows around a circuit for a given time, the energy supplied by the battery is equal to the energy transferred to all the components. The bulb, the resistor, the diode, whatever it is in the circuit. So now we've got some feeling for this, let's have a look at looking at some appliances, whatever they may be. We've got the same formula that we can actually work on to try and work out about our devices. We can look at one other one here, that energy simply is the power times the time. I know my power is volts times current, so we could write that one as E equals V times I times the time taken. We've got these formulas. We also learnt earlier about efficiency. And efficiency is the output over the input power times 100%. So if we know the input power, we know the efficiency, then we can work out the output power. Or we can work out the efficiency of a device. Now, what we can do is we can look on many devices and we can see how efficient they are. And when you buy a new device, then we often get a picture that looks something like this. We'll just pull it up for you. There's a little pause while we try and locate the picture. Alright, it'll come in a moment. And we've got the efficiency of our device, and we can see on the things that we buy a little table, and these are in different colours, and we have the sort of colours going down here from green to red, and as we go down here we move from the most efficient to the least efficient, and there we have one of those things that comes on a particular device. I very carefully managed to try and collect one of these off of my new refrigerator and show you, and I've put it down somewhere and I can't find it. And we could see that this device here is an A device. It is quite efficient. If we look at other devices, then we can see that they may be quite efficient or not. I remember looking at some devices we had in the church and having a look at some of the devices in the college where I worked, and they came down as G devices. They were very old, not very efficient. And when they were replaced with something more modern, more efficient, then it became a lot better because less money was wasted. So we look at these devices, they've got this efficiency rating, and the efficiency rating normally ranges from A down to a monstrous G. But gradually devices have become more efficient, and we often find we get devices that are going to be A plus or plus plus or even A plus plus plus. And we have to try and work out how useful it is to buy a device like this. So why wouldn't you always buy the most efficient device? Well, this one could be more expensive. If this is much more expensive, then the savings you might make aren't necessarily worth it. So let's have a look at a little scenario. I want to buy a fridge, and I've got a choice of two fridges. They're called A and B. A is very efficient. It's an A plus with 3 pluses. The other one is only A efficient. Now I start to go through and have a look on this particular symbol. Wrong picture. It's alright, my son took it away from me. There, it comes back. And if I look at the efficiency of this, then we might get here the energy consumption per year, and it's in kilowatt hours per year. And when we look at these kilowatt per year, we might find that this, let's say, is going to use 80 kilowatts per year, 80 kilowatts. And this one is going to use, let's suppose, 100. So over the year, I'm going to save 20 kilowatts of energy. But if I suppose this costs £500 and this one costs £250, then I've got to save £250 over the lifetime of this refrigerator to see that it's worthwhile. So £250, how much does 20 kilowatts cost? And over a lifetime, how many of those do I need to try and get that extra money back? And this is a big problem that we've got when we're looking at these type of devices. Sometimes the most efficient isn't necessarily the cheapest overall, because we want to look at the lifetime of our product. If this product was only going to last me a year, then I'd have spent more money on buying it, but it would be cheaper to run, but only very fractionally cheaper to run. So in 1 year here, I would spend £500 on the fridge, plus, let's suppose we're going to say it's going to cost £20 in electricity.
We're going to say Merry Christmas again by Ivan Rosenberg on
Now,
Thompson Music.
what we've got is... It's alright, they're just trying to deal with the Alexa device deciding to play lovely music. If I want to run this for 5 years, then it's going to cost me still the same amount to buy, but it's going to give me £100 worth of electricity. Compare that with my other fridge that might cost me 1 year to buy. It might cost me this time £250 to buy, but in electricity it might cost me £25 to run. And in 5 years it would still cost the same amount to buy, and it will have only have cost me here an extra £25 to run. This would work out cheaper than that one. So devices aren't always the most efficient, isn't always the cheapest. Something we do have to think about. But we also do have to think about costs of running things. Generally, a product costs so much to buy, but then if you're going to run it for several years, you normally would recoup that money back. And so it's often cheaper to buy and run a more efficient device. And it's also very good for the environment. Let's have a look at working out the efficiency of a device. Let's suppose we run something at our standard 230 volts, and I've got a 12 amp motor, and it's going to run at 50% efficiency. And what we want to try and do is work out how efficient and how much power and everything else about this. So let's work out some things about this sum. So we want to work out the power. The power is the voltage times the current. So this is going to be 230 times 12. Looking at my calculator, then this is going to be a simple sum of 230 times 12, which is going to give me 2,760. Watts, because we're measuring this power. So we've got the number of watts. Now, if we've got a machine that's only 50% efficient, then if I'm trying to work out what this will be the input power. Our output power is simply going to be 50% here. We could have chosen any number here. I've chosen 50%, and it's going to be that divided by of 100%, so it's only going to be, in this case, a half, which I'm sure you could work out. Had I chosen something like 60%, then we would times this by 0.6, and if it was only 10%, then we times it by 0.1. This was our question, 0.5. So our output power is going to be our input power times by 0.5, and working that out gives me 1380. So I've got my equation that we had, the efficiency. I've just used this. Efficiency here is 0.5 or 50%, and that's going to be our power we have when we've got this. Our efficiency is going to be our output over our input, which in this case was our input. I wish I could remember to look at the screen sometimes. And our output. Now, how much energy is wasted? And if we try and calculate how much energy is wasted, it's going to be 2,760 minus 1380, and we know it was a half, so it's going to give us 1380 watts of energy are wasted here per second. And that device really wouldn't be well worth trying to run. So over the last few lessons we've had a look at different sorts of properties of electricity, and we've ended up here looking at today appliances and efficiency and some other calculations. I hope you found that useful. Next time I want to try and go on and have a look at molecules and matter, starting to have a look at density. If you found this useful, then please subscribe, and I will see you next time. Take care and stay safe.